So, you've probably heard about ionic bonds, right? Where electrons get completely transferred. And covalent bonds, where they're shared. But what about metals? Well, they play by a whole different set of rules. Today, we're going to dive deep into the very cool and powerful world of metallic bonds to figure out what makes them the literal backbone of our world. Okay, let's put on our detective hats for a minute. We've got our subject, metal, and it has some very particular, very interesting properties. You know, it conducts electricity, it's got that classic shine, and you can bend it without it snapping. These are our clues. So the big question is, what's the secret? What's going on inside? I mean, really think about that for a second. You can take a simple paper clip and twist it into all kinds of shapes. But have you ever tried to do that with a salt crystal? No way. It just shatters into dust. The answer to this whole mystery, the reason for that huge difference, is hidden way down at the atomic level. And here we go, our first major clue. Inside a piece of metal, atoms aren't just floating around randomly. Nope. They arrange themselves into this super neat, organized, repeating pattern. It's called a crystallattice. And this perfect structure, well, it's the launching pad for everything that makes a metal a metal. And that organized lattice structure leads us directly to the solution to our mystery. It's an idea that's so perfectly descriptive, it's almost beautiful. It's called the sea of electrons. So how does this sea even happen? Well, once those metal atoms are all packed together in their lattice, their outermost electrons, they get a little restless. They actually break free from their home atoms, and they stop belonging to any one atom in particular. Instead, they form this free-flowing, mobile sea of negative charge that surrounds all the atoms, which have now become positive ions. And this is the really wild part. A metallic bond isn't just a connection between two atoms. It's a huge collective attraction. You have this whole grid of positive ions being held together tightly by this entire sea of shared electrons. It's not a handshake between two atoms. It's more like a giant group hug, a true community bond. Okay, so now we've got the model. Let's use it to crack the case and unlock the secrets of our metal's superpowers. Remember those clues from the beginning? Conductivity, bendability, that signature shine? Turns out the sea of electrons explains all of them perfectly. First up, conductivity. There's a reason we use copper for all our wiring, and it's all because of that electron sea. It's basically a superhighway for electricity. You apply a voltage and whoosh, those free-moving electrons just surge through the metal, carrying the current with them. Without that mobile sea, you get no flow. It's really that simple. And here we go, we've solved our original mystery, the paperclip versus the salt crystal. In an ionic solid like salt, when you apply force, you push the ions around. Suddenly, you get positive ions lined up next to other positive ions. They repel each other like crazy, and bam, the whole thing shatters. But in a metal, the positive ions just glide past each other, totally cushioned by that fluid electron sea. The bond doesn't break, it just bends and it taps. This is why that sea of electrons model is so brilliant. It acts like a flexible but super strong metallic glue. It doesn't matter how you push or pull on the ions, that sea of glue just holds everything together. This is what allows us to hammer metals into thin sheets, like aluminum foil. We call that malleability. Or stretch them into long, thin wires. That's ductility. And the final superpower, that metallic shine or luster, where does that come from? You can probably guess. It's the electron sea again. When light hits the surface of the metal, those free-moving electrons absorb the energy, get excited for just an instant, and then immediately spit that light right back out. This constant, rapid-fire absorption and re-emission is what our eyes see as a shiny, reflective surface. So, okay, this is some cool chemistry, for sure. But why does any of it really matter? Well, it matters because this unique bond, this sea of electrons, is the very reason metals have been able to, quite literally, build our entire modern world. You know, looking at this chart really puts it all into perspective. With ionic bonds, electrons are just transferred. In covalent bonds, they're shared, but only between a couple of atoms. But then you look at metallic bonds. The electrons aren't just shared, they're shared by every single atom in the entire piece of metal. That is the ultimate game changer. And that fundamental difference is exactly why metals are everywhere. That mobile sea of electrons, that gives us copper for our electrical grid. That flexible metallic glue, it gives us steel for our skyscrapers and bridges. It gives us the aluminum that lets us build cars and airplanes. Heck, even the simple beauty of a gold ring is just its electron sea playing with light. It all comes back to the bond. So if there's one thing to remember from all this, it's got to be this. The sea of electrons is way more than just a clever name. It's the simple, powerful idea that explains everything that makes a metal do what it does. It is literally the source of all its superpowers. And this leaves us with a pretty incredible question for the future, doesn't it? Humans have been mixing metals into alloys for centuries, but now we're finally understanding the deep principle at play. We're not just mixing metals anymore, we're learning how to design brand new seas of electrons. So what amazing properties, what technologies we can't even imagine yet are waiting for us to discover as we get better and better at engineering these seas at the atomic level?